Hello guys, today my group will be covering on the topic of horizontal well testing. So in this topic we will be covering basic definitions on how horizontal well test is done and the flow regimes in it and basic calculations regarding the flow regimes. So first of all, the first part will be presented by my group mate, Fong Yong.
Hello guys, my name is Fong Kam Yao and our group topic is horizontal well testing. And for my part, I will be in charge of the introduction of horizontal well. So to give you guys a brief idea about what horizontal well is. Okay. So this is introduction to horizontal well. The major purpose of having horizontal well is to enhance reservoir contact and hence increase the well productivity, because you will have a more flow area, so your productivity will be increased. However, for horizontal well, it's more difficult to interpret well test data because of 3D flow geometry. In horizontal well, you will need to visualize the well in a 3D form, and for horizontal well, several flow regime can occur. So I will explain to you what is the flow regime that will occur. So this is your horizontal well. This is a diagram. So in horizontal well, we assume the formation is a rectangular box, and x-axis is in the direction of perpendicular to the well, it's 90 degrees. Y-axis is parallel, and z-axis is the thickness. And for all the parameters here, we need to pay attention to this LWD, which is the horizontal well length, this part. And move on, we we can look at the factors that complicate the horizontal well interpretation. First, for horizontal well, the skin is not uniform. For this part and this part, you might have a different skin, and the selective completion along the horizontal well. For this part, you might have a open hole completion, and for this part, maybe a screen, or for this part, is different completion technique. And for the third point, heterogeneity in vertical direction as well as lateral direction. Just like a diagram here, you will have different probability for different direction. Next, I will be explaining to you about the different flow regime. So we have three different flow regime: early radial, early linear, and late radial. So you can see the pattern here from radial to linear and then change to radial. And this is the first one, the early radial flow regime. So it is the first stage before the pressure transient encounter either of the vertical boundary. Before the pressure disturbance touch the both vertical boundary, that's where early radial. And for early radial, the pressure transient will spread like a circular, but it's more to elliptical in a real situation because the x direction permeability is lower than the z direction permeability. I mean the x direction will have higher and z direction will have lower k. And next we will have a early linear flow regime. So after is the pressure disturbance keep on increasing, and then eventually it will touch the both boundary here, and then when that happen, the flow will act like as if it's in a straight line. It's a linear form. So this is where the early linear flow, you can see the description here. And for next flow, we have the late radial flow regime. So when it touches both boundary, the when it spread to the left and the right side, eventually it will form like a semicircle here. Yeah, and then the flow will be behaving like as if it is a radial. You can see the semicircle here, like this diagram also. So once an effect become important, a transition period is followed by late radial flow regime. So this flow regime will continue until it touches the both of the end of the boundary here. And next I will explain about the pressure behavior of horizontal well. So this is it. So to investigate the pressure behavior, we will plot the del P over, this is the P derivative of P is the P prime. So I will look at about we will focus about this line. So for early radial, our slope is 0. You can see this is the flat. And then for intermediate linear, we'll have half slope. It's like this is 2, this is 1, so you get a half here. For late radial, you get a 0 again. For the first part, it will be account for the well bore radius, a well bore storage effect. So that's all for me. Thank you very much. For the next part, my group member will be explaining to you different flow regime and different calculation. So okay, thank you very much.
For this topic, we're going to discuss about early radial flow regime in fluid flow in horizontal wells.
So what is early radial flow regime? The early radial flow regime occurs before the area drained or the pressure transient caused by this production encounters either of the vertical boundaries of the reservoir, considering the well producing at a constant rate.
So these are the figures for early radial flow regime. For figure 1a and figure 2 shows a radial flow pattern penetrating out in the reservoir. Actually, however, this flow pattern is likely to be elliptical like in figure 1c, moving further into the reservoir at a given time in the higher permeability x direction than in the lower permeability z direction. This phenomenon causes no significant complications in our analysis.
So these are the formulas that will be used in the calculations for the early radial flow regime.
Hello guys, next we'll be looking on intermediate linear flow regime. This intermediate linear flow regime is the second largest flow regime after the early radial flow regime. So this duration of the second major flow regime length is directly related to the effective length of the horizontal well. Basically, this length of the well bore must be greater than the height of the reservoir for this flow regime to occur. So the horizontal well will generally be long compared to the formation thickness. A period linear flow may develop once the pressure transient reaches the upper and lower boundaries of the well. Okay, moving next, look into the flow time equation. What is this flow time equation? This flow time equation is used to quantify the effect of linear flow regime. When does it start? When will it end? Why should we know this? Because first we need to know that whether our well is long enough for this linear flow to be significantly last. For example, if the period only lasts for 3 hours, it's not possible for us to make the well test. So we use this to test how long will this effect last. So first we have the Good and Tambi-Nayagam proposed solution, which gives this equation right here, which shows that when will this flow regime end. Second, we have this equation here proposed by Ode and Babu, which shows when will it begin, and this below your equation shows when will it end. So, and then if you notice, there are somewhere we have d here. So this d is equal to h minus dz, height of reservoir minus the length of reservoir from the top to the center of the well bore. So for example, if they give you question like they give you few parameters and they ask you to quantify the effect when how long will the period last, then you can use any of this equation. Most probably use 3 of these, and then you'll get when will it begin and when will it end. You get a range, so you can assume the range. So if the range is long enough, it means that our well bore is long enough, and we can also carry out the well testing to this well. Okay, next we'll look few equations and calculations. So first we have a drawdown test. So in case you are doing a drawdown test on this linear intermediate linear flow regime, first this is the general equation. As you can see, this general equation you can use to form a straight line equation. So this become y equals to mx plus nc, the intercept. So automatically you know if you draw a line of pi minus pwf delta p versus with the square root of t, okay, because here the x is actually a square root of t. So if you can plot delta p versus square root of t, what you'll get a straight line. From that you can get the gradient which represents this term here. You can see the same term. Okay, so once you already get the gradient, you can use it to get some other equations. I'll show you later. Second, you can see this is what we call pseudo skin factor caused by partial penetration in the vertical z direction. Okay, so this is the formula for it. And then you have product of producing well length square and permeability L square ky. Okay, and this is the formula for this. We notice there's the m here, so this m comes from the m that you find from plotting delta p versus square root of t. So once you put this m here, you will get the product of producing well length square and permeability. Next, what you need to do is, in your graph you have to extrapolate your line, okay, for it to intercept the delta square root t when it is equals to 0, basically a 0 point at delta t. So what do you get? Basically, as you know, when x is 0, y, whatever the line crosses at y axis, we call it y-intercept. So this is for you to get the y-intercept. Okay, for that you can find this term over here. So once you get this y-intercept, it equals to whole term here. So you can find this as skin. So how do you find? You use this equation, and on top of here you substitute your delta p of 0h time when t is equals to 0, the one you get from the y-intercept, and here you substitute your partial pseudo skin factor zz, and then you can get your s. So this is for drawdown. Next, for build-up test, we have two different types. One is an infinite and a bounded. The bounded reservoir, the solution is similar to the not very similar, but something similar to the drawdown test, so I'll not be elaborating on that. For this build-up test, for the infinite reservoir, where the reservoir is acting as though it's infinite, so we have this general equation. Again, you can form a straight line equation. This is the m, x, and this is the z or intercept. Okay, and when intercept gamma 3, okay, this is the formula where you can get this gamma 3. Okay, the intercept, and this is the formula for you to get the gradient, but usually you don't use the formula, you can use the graph and get your m. Once you get this m, substitute in this equation and get your equivalent permeability in vertical plane, kv ky. Okay, so once you get this, you can get the skin factor to this equation right here and substitute the m here, and this is p1 hour minus pwf. Okay, so that's all for a build-up test. So next I'll pass it to my friend to continue on the late radial region.
Fluid flow in horizontal wells, late radial flow regime. What is the late radial flow regime in horizontal wells? The late radial flow regime flow exists when length of horizontal well is shorter enough than the formation thickness and the flow across the tips of well becomes considerable. This flow regime is also called horizontal radial flow regime. Similar flow behavior also occur in vertically fractured well. It's also known as pseudo-radial flow that established at the late time. This period ends when the lateral boundaries affect the fluid flow, as shown in figures. As shown in figures, the fluid flow converges from all directions toward the wellbore. And these are the formulas that will be used in the early radial flow regimes.